Honors Chemistry. We are starting a new unit. This is Unit 3 on gas laws and the properties of gases, and Lesson 16 is the first lesson in that unit, and it's called Basic Gas Laws. So, the kinetic energy is the energy of motion. Anything that moves has kinetic energy. If the kinetic energy overwhelms the coulombic attractions, that's what attracts molecules to each other. For example, water molecules have a positive end and a negative end. They're polar. We've studied that. And the positive end of one molecule tends to stick to the negative end of the other. These are not real strong attractions, though. And if you can put enough energy, usually heat energy, into water by heating it up, causing it to boil, then you can give it enough kinetic energy, enough motion energy for the water molecules to break apart from each other. If the kinetic energy overwhelms the coulombic attractions between the molecules, then the molecules separate and exist as a gas or a vapor. So a gas is simply when the molecules are separated, and oftentimes we think of a gas as floating in the atmosphere, just like air molecules. They're also in gas form. Has nothing to do with gasoline that people put in their car. It's just a coincidence that those two have a name that's similar, but that's not the same thing. Okay, so the study of gas laws treats atoms, molecules, or ions in the gas state as though they're little balls. And we don't really care about protons, neutrons, and electrons. We've always talked about those, but when studying gas laws, we really don't care about those. We just treat the O2 as though it's a little ball, and it's just floating around in space, and it's bouncing off other little oxygen molecules or other kinds of molecules, or it's bouncing off the walls of a room or of a container. Since the gas can be either atom, molecule, or ion, we use the generic term particle. So we just call any of those things that are gas in gas form. We just refer to them as particles. So gas particles don't randomly change direction. You must imagine that these particles are changing direction for one of several reasons. They're encountering other particles. So here you see 4 of them kind of floating around, but imagine that there were 400 of them there, and they're constantly bumping into each other. So that's why they're changing directions. They don't just mysteriously change directions. So they do it because they're encountering other particles that you can't see, or they're bumping off the sides of a wall or of the container. And this gives the particles their apparent random motion. Also, if you heat them or cool them, that will cause them to speed up, to slow down, and that causes them to change their paths, change their directions as well. So gases can take part in chemical reactions. So example, 2H2 gas plus O2 gas produces 2H2O, and the H2O could either be gas or liquid, but in this case, since we're studying gases, we're going to say it's gas. That means it would be water vapor. So those G's stand for gas. They don't stand for grams in this context. That's the state of matter that these molecules are in. So water can be produced from hydrogen gas and oxygen gas. In this unit, we are only interested in how gas particles behave due to 4 factors. The first one is the pressure. How much pressure they're exerting on the container they're in, and how much pressure is being exerted on them. The temperature, the volume of the container, how big the container is, and the number of particles, and we measure that, of course, in moles. How many of these groups of 6.022 times 10 to the 23rd, so how many particles there are. Pressure is the amount of force per unit area, so that's a definition you learned in physics. Force is a push or a pull, and if you put that force on a very small area, that will be a greater amount of pressure. So the pressure of a gas can be thought of as the frequency with which gas particles hit the sides of containers. So kind of keep that as a loose definition of what pressure is. It's how often they hit the sides of a container. The units of measure for gas variables are temperature is measured in Kelvin, volume is measured in liters, moles is measured simply in the number of moles, and pressure has 5 different units of measure. One is called atmospheres, pascals, kilopascals, torr, and millimeters of mercury. Those evolved from different fields of study, some of it being atmospheric science or meteorology or chemistry or physics. So they have these different ones, so you're going to learn how to convert between them. Now for temperature, Kelvin, if the temperature is given to you in centigrade, generally speaking, you need to convert to Kelvin. If the volume's given to you in milliliters, commonly volumes in chemistry are given in milliliters, that's 1/1000th of a liter, you have to convert that to liters. And then number of moles is what it is. So 1 atmosphere is the normal air pressure at sea level where we are. So the air pressure that you feel on your skin right now, on your body, you don't feel any air pressure, but it's there, believe me, is 1 atmosphere. If you go to higher elevations up into the mountains, then it's less than 1 atmosphere of pressure. The following are conversions between the units of pressure. So 1 atmosphere, which is what we feel here at sea level, is equal to 760 millimeters of mercury. In other words, if you have a pressure gauge called a barometer, or there's another one called a manometer that's used in chemistry, if it can get the mercury to raise up 760 millimeters, that's basically 3/4 of a meter, that would be considered to be normal sea level atmospheric pressure. That would be the equivalent of 1 atmosphere. They decided to give it another name, torr, so that's also equal to 760 torr. In pascals, that's a different unit of measure. It's 100 to 1,325. And in kilopascals, that's 1,000 pascals. It's 101.3 kilopascals. So all of those are equivalent to each other, and they equal roughly the pressure that you feel right here at sea level. In the same way that you made conversions between grams and moles, you make conversions between any two of the measures above. Why there are 5 different units of pressure is something you don't need to understand. Just know that how to convert between them. So we'll do some practice on that. All right, so here are the 5 conversions. So we're going to just run through a few quick examples. So examples of pressure conversions. So how many kilopascals in 2.3 atmospheres? So you do these the same way we did the stoichiometry. Over on the far right side, what you don't know goes at the end of the equation. So some number of kPa. Way over on the left side, at the beginning of the equation, it's 2.3 atmospheres. Now you just need to look up above and find the relationship between atmospheres and kilopascals. Those are the only 2 that you need to use for this question. So 1 atmosphere equals 101.3 kilopascals. Now you just have to decide which one goes on the top and which one goes on the bottom. And so it looks like this. You start with 2.3 atmospheres. You need kilopascals on top. You need atmospheres on the bottom to cancel with atmospheres. So you end up with kilopascals in your final answer. And you just do the math on that and you get 233. Okay? You don't have to write these down, but it doesn't hurt. Just try to think about how you would set them up. How many millimeters of mercury in 1.05 atmospheres? So you simply have to go up to the top, look at the relationship between millimeters of mercury and atmospheres, and it's 1 atmosphere equals 760 millimeters of mercury. You need to end up with millimeters of mercury. You need to start with 1.05 atmospheres. So which of those conversions goes on the top and bottom? So the atmosphere has to go on the bottom, so it cancels. You have millimeters of mercury on the top, and then you just do the multiplication and you get the final answer. One more. How many torr is 98,600 Pascal? So you go up to the top, find the relationship between torr and Pascal. 760 torr equals 101,325 Pascal. So what do you start with? 98,600 Pascal. Which one goes on the top? Which one goes on the bottom? You'd have to have Pascal on the bottom to cancel out. So you end up with your final answer in torr. So that's how you do these conversions. They're not very hard. So temperature is the average kinetic energy of the molecules. This translates to meaning that the higher the temperature, that higher temperature increases the speed of the molecules. So there's a molecule, a hydrogen molecule, just moving around inside of a container. And if you heat it up, then you're going to get the same molecule moving at a faster speed. All right, so temperature, average kinetic energy, because if you had a lot of hydrogen molecules, let's say you had a mole, they're not all going to be moving at exactly the same speed. Some are going to be moving a little faster, some are going to be moving a little slower. So it's the average kinetic energy that is in the molecules. It doesn't just have to be a gas, it could be a liquid or a solid. So that's why I say a metal bar could feel hot, is it has temperature inside. It has kinetic energy. The molecules inside of a metal bar are actually wiggling around and shaking and moving. And we'll talk about the different types of motions that atoms and molecules and particles in general can have. So temperature is the average kinetic energy of the gas particles. Kinetic energy is given by a formula that you probably learned in physics. Kinetic energy equals 1/2 mass times velocity squared. M is mass, V is velocity, just think of it as speed. By increasing the temperature, we increase the average kinetic energy of the particles. Since the mass of the particle, in this particular case it's a hydrogen molecule, since the mass of the particle remains constant, then increasing the kinetic energy increases the velocity of the particle. So if you look at that equation up above, K equals 1/2 mv squared. If Ke gets bigger and m has to stay the same, then the only thing on the other side of the equation, on the right side of the equation, that can get bigger is the velocity. So that means the molecule has to, or the particle has to speed up. So let's say we have particles with two different masses in a container at the same temperature. That means they're going to have the same kinetic energy if they have the same temperature. So assume the following, that the mass of particle A is 2 atomic mass units, the mass of particle B is 8 atomic mass units, and let's just say the kinetic energy that they both have is 16 joules. Because they're at the same temperature, they have the same kinetic energy. So the formula for kinetic energy is shown there again. So both particles have the same kinetic energy, 16 joules, so we can compute the velocity of each particle. So for particle A, kinetic energy is 16. That equals 1/2 times the mass, which is 2 for particle A, times the velocity squared. So you just have to do a little algebra work here and solve for the velocity of particle A, and that would give you 4. It doesn't matter what the units of measure are. It could be meters per second, but whatever we want to say it is. What we're trying to find here is the relation of the speeds of the two particles, not a specific number. Okay, let's do particle B. Also has a kinetic energy of 16 equals 1/2. Now the mass of particle B is 8 times the velocity squared. So again, you solve for the velocity for B and you get VB equals 2. So particle A has a velocity of 4. Particle B has a velocity of 2. So particle A's velocity is twice what particle B's velocity is. So think about what that's saying. It's saying that the heavier particle B, is 4 times as heavy as particle A, 8 AMU to 2 AMU. Then its speed is 1/2 that of particle A, 2 versus 4. So the heavier particle, as you might expect, moves slower. So let's see if we can find a mathematical relationship here. So the 2 AMU particle moves 2 times faster than the 8 AMU particle. So the 2 AMU particle moves 2 times faster than the 8 AMU particle. This leads to the following relationship for two gas particles called Graham's law of effusion. We'll talk about what effusion is in a later lesson. It's basically how fast molecules move. You can just use that definition for right now. So the speed of the lighter particle compared to the heavier particle is the mass of the heavier particle divided by the mass of the lighter particle, and then you take the square root. So in our previous example, the heavier particle was 8. The lighter particle was 2. So 8 divided by 2 is 4. The square root of 4 equals 2. So what that's saying is the lighter particle is going to move twice as fast as the heavier particle if the heavier particle is 4 times as heavy as the lighter particle in this case. So this just demonstrates Graham's law of effusion. Okay, relationships between temperatures. There's 2 temperature scales we use in this class, the centigrade scale and the Kelvin scale. We do not use the Fahrenheit scale, which is what's used here in the United States. If you watch TV and watch the weather report and they say that the temperature outside is 70 degrees, that's in Fahrenheit. We don't use that scale in chemistry. So we do use the centigrade and the Kelvin scale, and the centigrade, as someone mentioned in class, it's also called the Celsius scale. Either one, they're both exactly the same, centigrade and Celsius. So let's look at the two scales. What they did when they came up with the centigrade scale, it's part of the metric system, and the metric system is based around the properties of water. So they just made a very logical choice. They said there's three states to water: solid, which we call ice; liquid, which we just call water; and vapor, which we call steam or water vapor. So the dividing points between the solid and the liquid, they just defined as 0 degrees. And then the dividing point between the liquid and the vapor, which is where water boils, is 100 degrees. They just arbitrarily assign those two numbers at those 2 points. That's what's called phase changes. When it goes from solid to liquid or from liquid to vapor, those are called phase changes. So they just assign 0 to the phase change between solid and liquid, and 100 to the phase change between liquid and vapor steam. And then they just divided that distance into 100 little pieces. That's what centigrade means. It means 100 divisions is really literally what centigrade means. 100 gradations or divisions. Okay, so that's the centigrade scale. Scientists, however, said we want a scale for science where 0 really means 0. It is the absolute lowest temperature that you can have in the universe. You can't have anything below 0 on this scale. So they came up with the Kelvin scale, and the Kelvin scale, 0 is actually the lowest possible temperature in the universe. It's when you pull all the energy out of an atom, so the electrons just literally collapse into the nucleus. They have no more energy. Basically the atoms have died. They have no more motion. So 0 on the Kelvin scale is the lowest possible temperature in the universe. You can't have a negative number on the Kelvin scale. So now if you look at the two scales, you'll notice that the difference between the freezing point of water and the boiling point of water is 100 degrees, 0 to 100. On the Kelvin scale, the difference between the freezing point of water and the boiling point of water is also 100 degrees, from 273 to 373. So a degree on the centigrade scale is the same distance, it's the same amount of kinetic energy as it is on the Kelvin scale. So a degree is the same on both scales. What's different is what they decided to call 0. On the centigrade scale, 0 is the freezing point of water. On the Kelvin scale, 0 is the absolute lowest possible temperature you can have in the universe. So if you line the two scales up side by side as we see here, you can see how they match up. 0 degrees centigrade equals 273 Kelvin. Negative 273 centigrade is the lowest possible temperature you could have in the universe, which is equal to 0 degrees Kelvin. And if you go from the freezing point up, you go from 0 to 100 on the centigrade scale, and you go from 273 up 100 to 373 on the Kelvin scale. So absolute 0 is the lowest possible temperature in the universe. It is 0 K on the Kelvin scale and negative 273 centigrade on the centigrade scale. A degree on both scales is the same change in kinetic energy. The only difference is what each scale defines as 0. Alright, so to make the conversions, it's a real simple formula. To get Kelvin, you simply take the centigrade temperature and add 273 to it. To get the centigrade temperature from Kelvin, you take the Kelvin temperature and subtract 273. Technically, on the centigrade scale, you refer to the numbers as degrees. On the Kelvin scale, you don't, but it's not really a big deal. So you would say, for example, 100 degrees centigrade, but on the Kelvin scale, you would refer to 373 Kelvin. You don't use the word degree. It's not really a big deal, but you might as well learn that. Okay, so the simple formula to make the conversion, I give you a few of those problems on the assignment. It's pretty easy. So here's some examples. Convert 25 degrees centigrade to Kelvin. So 25 plus 273 is 298. That's one you're actually going to see quite a bit in chemistry in problems in this class in the future. 25 is it's basically room temperature, and so it's a pretty standard temperature to use in chemistry problems. So you'll get used to 25 degrees centigrade or 298 Kelvin also. Convert negative 35 centigrade to Kelvin, so negative 35 plus 273 is 338 Kelvin. Convert 313 Kelvin back to centigrade, so 313 minus 273 equals 40 degrees centigrade. and convert 260 Kelvin to centigrade. 260 minus 273 would be negative 13 degrees on the centigrade scale. Again, you can never have a negative number on the Kelvin scale, never. Volume is the amount of space an object occupies in 3 dimensions. If it's 2 dimensions, it's called area. If it's 3 dimensions, it's called volume. So in some cases, the volume can change, such as with a balloon. It can get bigger or smaller. In other cases, the volume can be fixed, such as a glass or metal container. So a lot of times in a problem, it will refer to a rigid container. If it says it's a rigid container, automatically in that problem, you know that the volume can't change. The volume has to stay the same throughout the problem. So volume is measured in liters. Often in chemistry, volumes are measured in milliliters. There are 1,000 milliliters equals 1 liter. So in some of the problems, you're going to have to convert from milliliters to liters. It'll be necessary to do that. So convert 467 milliliters to liters. So there's 1 liter equals 1,000 milliliters, and you have 467 milliliters, so the milliliters has to cancel, and you end up with 0.467 liters. So 467 milliliters is 0.467 liters. Another important volume relationship is between centimeters and liters. 1 cubic centimeter, centimeter is roughly a half an inch, not exactly, but kind of close if you think of about a half an inch, a little bit less than that actually. And if you'd make a cube out of that, so a centimeter by a centimeter by a centimeter, that's a cubic centimeter, that's the same as 1 milliliter. So it allows you to convert between a unit of distance, which is centimeters, by cubing the centimeters, and volume, which is milliliters. So 1 cubic centimeter equals 1 milliliter. Okay, there's one major formula that relates the 4 variables of gases, and it's called the ideal gas law. And what it simply says is pressure times volume equals the number of moles times R, which is called the gas constant, the ideal gas constant, times the temperature. And this is the single most important formula in the study of gas laws. So PV and T and N have been defined previously: pressure, volume, temperature, and number of moles. R is called the ideal gas constant. And there's actually 2 different versions of the ideal gas constant, but for this particular unit, it's going to be 0.0821, and it's liter atmospheres divided by moles Kelvin. So the purpose of this constant is that it cancels the units of measurement, so only the units of the final answer appear. You could think of it, we've talked about conversion factors, where one part of it cancels. Well, just think of this as a whole bunch of conversion factors all rolled into one number. So what it does is it makes everything cancel out in that problem. In PV equals nRT, it makes everything cancel out except the units that you want for the final answer, and it will always work out that way, no matter how you rearrange those variables in that equation. So the ideal gas law is the central formula for the study of gases. An ideal gas is a gas in which the particles don't interfere with each other. So if you could take just a single helium atom and stick it in outer space with nothing else around, no other atoms around, that would pretty much be an ideal gas. There's nothing to interfere with the movement of that particular atom. So the ideal gas law, PV equals nRT. Pressure is in atmospheres. Volume is in liters. N is the number of moles, so that's simply a number. And the temperature T is in Kelvin. Now, how did you know that? If you go back and look at that ideal, the gas constant, liter atmospheres over moles Kelvin. So if we go back to that, so you see down there in the bottom left, liter atmospheres over moles Kelvin. That tells you what you really want to look at when you look at any constant like this, is what the units are, because it tells you what units you have to have your variables in. So for example, we talked about the 5 different units of measure for pressure. One of them was atmospheres. There's also torrs, millimeters, mercury, pascals, kilopascals. If you were given units in torr, you would have to convert that into atmospheres in order to use this equation, because that gas constant is in atmospheres. If you were given a temperature in centigrade, you would have to convert that to Kelvin, because again, the gas constant has Kelvin in it. So what you want to look at with constants like this is what are the units in that particular constant, and that will tell you what units you have to have all of your variables measured in. So think of the gas constant as several conversion factors wrapped into one number. R causes all the units to cancel except the one needed in the final answer. So let's say we wanted to take the equation and we wanted to solve for pressure. So mathematically, what would you do? You would divide both sides by volume. So you'd have pressure equals nRT over V. So that would be solved for pressure. And what the R would do is it would cancel out all the units except atmospheres, which is what you want for your final answer if you're looking for pressure. Let's say you wanted to solve that equation for temperature. So mathematically, you would divide both sides by nR. So temperature would equal PV over nR. And again, the R would make all the units cancel except Kelvin, which is the unit of measure for temperature. So it just works out that way every time, that R will make the units cancel out, so you end up with the units in your final answer that you want for the variable that you're trying to solve for. So the ideal gas law, PV equals nRT. Think of the gas constant as 6 conversion factors wrapped into one number. So example, if you solve for temperature, T equals PV over nR, the gas constant R will cause all units of measure to cancel except Kelvin, the unit for temperature. What happens to pressure when volume is increased? So now we're going to get into 3 laws that were developed independently by 3 different scientists. And they didn't know the ideal gas law, but we're going to use the ideal gas law to study them. So a fellow named Boyle came along and found a relationship between pressure and volume. So what happens to pressure when volume is increased? Assume all other variables remain constant. So for the next few slides, if the variables are in black, that means they're staying constant. If they're in red, that means they're going to change. So think about that. If nR and T have to remain constant, if you increase V, you have to decrease P by the corresponding amount in order to keep nR and T, N times R times T, to be the same number. So think about it. If you double V, double the volume, you'd have to cut the pressure in half. So double the volume, 1/2 the pressure, that would equal the same number, N times R times T. So if nR and T remain constant, then as V increases, P decreases. So there you see the arrows, how they work. Now, just drawing the arrows like that is a really good way to understand the relationship, but it doesn't tell you which is the cause and which is the effect. Decreasing pressure doesn't increase volume, but increasing volume will decrease pressure. So sometimes it's not clear what the cause and effect is when you see these relationships, but it'll tell you which way they will move. Okay, so P decreases because the particle hits the side fewer times. So let's go ahead. So here's a particle. It's moving at a certain speed. That means the temperature. If the temperature is the same in both of these boxes, both particles have to be moving the same speed. So here's a particle moving around at a certain speed, and you can see it's hitting the walls a certain number of times. Now, the particle in the other box, it's a bigger box. We've increased the volume, the size of the box. Now that particle on the right is moving the exact same speed as the particle on the left. But since it has a longer distance to travel, it doesn't hit the sides as many times, and therefore it's exerting less pressure on the sides of the container than the particle on the left. So by increasing the volume, the particle's moving the same speed, but by increasing the volume, the particle on the right hits the sides fewer times, so the pressure is decreased. This relationship between pressure and volume is called Boyle's law. What happens to pressure when temperature is increased? Well, just look at it mathematically. What's going to happen? If you increase temperature, what's going to happen to pressure? Just think about it mathematically. Well, if something on the right goes up, let's say by 2 times, let's say you double the temperature, then you're going to have to double what's on the right side. You're going to have to double the pressure to keep the equation in balance. So as temperature goes up, pressure goes up by the same proportion, by the same amount. In other words, you double temperature, you double pressure. If you triple temperature, you triple pressure. It has to go up by the same multiple. So if N, R, and V remain constant, then as T increases, P increases, and this is because the particle hits the sides more times. Again, just think of pressure as how many times does the particle hit the sides. So the relationship between pressure and temperature is called Gay-Lussac's law. So here you've got this particle over here. So it's moving at a certain speed because it has a certain temperature. Now on the right side, the box is the same volume, so we haven't changed the volume. V, N, and R are going to stay constant. So we put some fire under that now, and so now that molecule, because it has higher temperature, that means higher kinetic energy, which means it's moving faster. It has a higher velocity. So that means the particle on the right is hitting the sides more times, so it's putting more pressure on the sides of the container. So as you increase the temperature, you increase the speed of the molecules. They hit the sides more times, and that's an increase in pressure. Okay, what happens to volume when temperature is increased? So again, mathematically look at it. V and T. If T goes up, what happens to V? Well, they're on opposite sides of the equal sign, so if you double T, you'd have to double V. If you triple T, you'd have to triple V. You have to maintain the equality there because they're on opposite sides of the equal sign. So if N, R, and P remain constant, then as T increases, V increases. So think about that. The key here is the pressure. If the pressure is going to remain constant, that means the number of times that helium atom in the little balloon on the left hits the sides has got to be the same as the number of times the helium atom in the big balloon on the right hits the sides. But if temperature goes up, that means the speed of the helium molecule on the right is going to increase. So if it's going to hit the sides of a bigger balloon the same number of times as the one on the left, the balloon has to be bigger. So for the particle to hit the sides the same number of times, constant pressure, while moving faster, higher T, the volume must get bigger. This is called Charles' law. So if you look at that, and if you counted that, that's going around about one time every 2 seconds, okay? So from right now to right now, that's about 2 seconds. Now let's look at the one on the right. That one's also going around one time every 2 seconds. So from now to now, that was 2 seconds. But since the one on the right is moving faster, and it is because you increased the temperature, that makes it move faster, if it's going to hit the sides the same number of times, that means constant pressure, as the one on the left, then the balloon has to be bigger. The sides have to be farther apart so that it has to travel a farther distance. So this is the hot air balloon equation. As you increase the temperature, and remember it has to be a flexible volume like a balloon, as you increase the temperature you're going to increase the volume of the balloon, but the pressure stays the same. The pressure of these two balloons is the same because they're hitting the sides the same number of times per every second or every 2 seconds. Okay, what happens to pressure when the number of moles is increased? So if temperature, R, and volume remain the same, so the box is a certain size, the temperature is going to stay the same. But what we're going to increase is the number of molecules. So if T, R, and V remain constant, then as the number of moles increases, P increases because there are more particles hitting the sides. That makes sense. Pressure is how many times the particles hit the sides. If you have more particles, they're going to hit more times. So the relationship between pressure and number of moles is called Avogadro's law. So you can see since N and P are on opposite sides of the equal sign, if you double the number N, you also have to double the number P. If you cut N in half, you have to cut P in half. They have to remain proportional to each other. So there we have, let's just say we have that one hydrogen molecule going around and around. So it has a certain amount of pressure. It's hitting the sides a certain number of times every second or so, or every 10 seconds. Okay, so simply by doubling the number of hydrogen atoms, we double how many times they hit the sides. They're both going the same speed because they're at the same temperature. So therefore, you've increased the pressure because the sides are being hit twice as many times with twice as many molecules. So that's a very simple relationship between the number of moles and the pressure. Okay, so that takes care of the basic gas laws. Again, really Boyle's law, Charles' law, and Gay-Lussac's law are not nearly as important as the ideal gas law. And one thing you notice that the ideal gas law has in it, it has number of moles. And what we've been saying for the last 3 or 4 weeks is that if you're going to use a chemical equation, everything has to be in moles. So you have to be able to translate pressure, volume, and temperature into numbers of moles so that you could put the gas, an amount of gas, into the chemical equation so that you know how many moles that you have so that you can put that in the chemical equation to do some stoichiometry on the gas. And that's going to be the subject of the next lesson, is gas stoichiometry. Okay, so we'll see you on that lesson. This lesson, again, get past the test on Wednesday, April the 7th. Get past the test, or April the 8th, depending on which class you're in. That's Wednesday or Thursday. Get past that before you worry about this lesson, okay? This can wait, and you can do this Friday, Saturday, and Sunday, and get that in next week. Okay, I'll see you in the next lesson.